Let's mark up the feet of the altitudes of any triangle, the midpoints of the sides and the midpoints of the segments from the vertices to the orthocenter. Do you know why this composition is so impressive? It seems that this one and many other beautiful theorems were well known in ancient Greece a long time ago, and all we are left to do is reap the ancient fruits. But no, the 9-point circle was discovered by Euler, and lots of other surprising facts were found in the 20th century. For example, Morley's trisector theorem. The picture shows angle trisections. What do you think makes this highlighted triangle stand out? It is always equilateral. Frank Morley came across this wonderful property when he was studying cubic curves. One of the most concise proofs of this theorem was created by John Conway a couple of decades ago. Of course, he has plenty of other results, but today I also want to mention the Conway circle. Sketch an arbitrary triangle and extend its sides. Pay attention to the marks of equal segments. Eventually, we will have 6 points on one circle. Its center always coincides with the center of the inscribed circle. Here's another theorem that slipped away from Euclid and even Ptolemy. Let's look at the circumscribed circle of an equilateral triangle. Connect a point from one of the arcs with the vertices of the triangle. Notice anything particularly interesting? If you don't, then look at the lengths of the segments and you will probably figure it out. Surprisingly, Pompeiu's theorem was discovered only in 1936. Let's prove it. Follow the bottom triangle, rotating it 60 degrees around point A. Vertex C will move into B because the angle of an equilateral triangle is exactly 60 degrees. And point B will inevitably turn into E on BP. In the comments, try to explain why it is happening, and the theorem is proved. When we rotate segment AP, it turns into equal segment AE. Angle PAE is equal to the rotation angle. It means that triangle APE is equilateral, so the sum AP plus BC is equal to the sum PE plus BE, and this is actually the length of BP. By the way, do you remember the theorem named after Napoleon? We will certainly prove it in one of my videos later. As far as I'm concerned, similar fact about quadrangles was published only in the 20th century and was called Thébault's theorem. Let's draw outside squares on the sides of the parallelogram. Then the centers of these squares form what? Right, another square. Do you want one more marvelous proof based on rotation? Let's look at the triangle LBM and rotate it 90 degrees around point M. What do you think we will get in the end? Oh wow, it moved into triangle NCM. But why? Think about it. Regarding BM and MC sides, everything is clear. They are equal since they are diagonals of the square. The same happens to BL and CN. All you are left to do is show that angles LBM and MCN are equal. Try it, and if you won't succeed, then look at the description of the video. Eventually, segments LM and NM are equal because they overlap each other after rotation. The same approach works for other triangles, and it means that in the quadrangle that is particularly interesting for us, all sides are equal and all angles are right. So it is a square. Please notice that if we draw squares on the sides of an arbitrary quadrangle, then diagonals still be equal and will cross each other at right angle. This theorem was previously proved by Van Aubel, and in the 20th century, more general fact was found. Finally, let's draw the medians of a triangle. You probably know why they divide it into 6 parts with equal areas. But in 2000, a new and fantastic problem appeared. I will leave it to the animation. Think critically, do math, take care.